Let's understand what role the master plays in a Kubernetes cluster. Let's turn back to the diagram we drew a moment ago. Remember that a Kubernetes cluster consists of a large number of infra components. These infra components could just be bare metal machines, they could be virtual machines running in an on-premise data center, or they could be virtual machine instances running on the public cloud. It doesn't really matter. Once we have a large number of these instances and these together form a cluster, Kubernetes is going to designate one of these instances as a master and all of the rest as the workers. The master is now going to run a set of Kubernetes processes. These processes will ensure the smooth functioning of the cluster, and collectively these are called the control plane. Remember this word, the control plane of the cluster. This is something that you will see quite often. One quick note before we dive into the nitty-gritty of the master. A moment ago, I said that one node is going to be designated as the master. That may not always be true. In recent times, the trend is towards high availability clusters in which more than one piece of infra might be dedicated to run as the master. This is similar to high availability Hadoop clusters, for instance, where we have multiple master nodes and some orchestration software like Zookeeper running between them. But in general, in a Kubernetes cluster, we can think of the master as being one single VM instance which runs different processes to keep the cluster running smoothly. Let's now double click on the master and see what the different constituents of the control plane are. The first component of the control plane worth discussing is the Kube API server. This API server interacts directly with the user. The typical mode for using a Kubernetes cluster is that the user types up a YAML or JSON manifest. This manifest specifies the desired state of the system. This is then submitted to the cluster using a command line tool such as kube control. Under the hood, all that this is doing is making a RESTful API call. That API call in turn is going to hit this Kube API server. So the API server is going to digest the incoming post requests which are made by users of the cluster. It's going to parse the YAML or the JSON, and it is going to then go ahead and take action in order to bring the actual state of the cluster to match the new desired state of the cluster. The API server is by definition meant to scale horizontally, and in high availability clusters, this is the biggest component of the horizontal scaling. The API server is the front end of the Kubernetes control plane, or at the back end is a cluster store. Clearly, there is a whole bunch of metadata specified in those manifest files which are posted by the cluster users, and that metadata needs to be saved somewhere. That somewhere refers to the cluster store. This cluster store is built on top of etcd, which is a very popular distributed key value data store, and this serves as the single source of truth. This is where all of the information relating to the state of the cluster is going to reside. We've discussed briefly that the basic logical unit in Kubernetes is a pod. A pod is going to contain one or more containers. These are going to be tightly coupled to each other, and these containers are actually going to host the application. This is the heart of the compute. When users make requests for the creation or the management of pods, some entity within our master, within our control plane, is going to have to take action on those requests. And this entity is the scheduler. The scheduler or the kube scheduler is a component of the master which is going to effectively listen for new pod creation requests. When such a request comes in, the scheduler is going to have to make a match. It is going to have to assign some node, that is some underlying worker infrastructure, for that pod to run. This decision can be quite complex, as we shall see. Scheduling decisions need to take into account various requirements related to this particular pod, its affinity and anti-affinity specifications, data locality, the workload between different pods, their interference, and so on. The last and maybe the most interesting remaining component of the control plane is the controller manager. This controller manager is a kind of grab all for a set of different master processes. Those master processes have broadly the responsibility of making sure that the actual state of the cluster and the desired state of the cluster match each other perfectly. There are two possible choices for the controller manager. If this is a Kubernetes cluster which is running on the cloud, this controller manager is most likely going to be a cloud controller manager. If not, and if this is an on-premise or non-cloud Kubernetes cluster, this is most likely going to be a kube controller manager. In either case, there are going to be separate controllers for different aspects of matching the desired and actual state of the cluster. There will invariably be a node controller which has to take action if nodes go up or come down. There is going to be a replication controller which is going to make sure that the correct number of pods is actually in play. We'll have more to say on this in a bit. There will also be controllers for routing, that is various networking services. For volumes, we'll talk about volumes in a bit. They are ways of specifying state within our containers. In general, whether we have a kube controller manager or a cloud controller manager, this component is going to consist of a number of separate controller processes. Each of these processes is effectively a daemon or a process running in an infinite loop, which is comparing the desired state of the system to the actual state of the system and taking actions to bring the two into sync. Taken together, these four processes or these four entities constitute the control plane of the Kubernetes cluster. The first of these is the API server. This is what gets hit by user requests when manifests or JSON or YAML files are specified. The second is the key value data store for the metadata, also known as the cluster store. This is implemented in etcd. The third is the scheduler, which has to take action when new pod requests come in. And the fourth is the controller manager. And the controller manager could either be a kube controller manager or a cloud controller manager. In either case, the controller manager consists of a number of disparate processes which have to reconcile the actual and desired state of the system.